Hello. I seem to have returned. I have cropped the... I made some improvements this time around. I cropped the edges a bit. Let's see how it goes this time. Well, first to the introduction, what am I gonna do? I'm gonna work on my semester project. If I switch to the real life cam, it's that thing on the top right. As is written in my description, I'm an engineer and I'm studying to advance my understanding of programming industrial controllers. In school, we specifically have a Siemens controller. For ease of my speaking, I'll continue referring to the industrial controllers as PLCs, programmable logic controller. And my semester project consists of programming that red guy, which is a little high bay area model. You can picture that the left thing is a little crane that can move metal blocks around in the storage area on the right side of the red model. Then to the right of the red model, between the green bundle of cables and the red model, is a motor controller, which I have to sync up to one of the drive axes of the model. I'm not required to have it move at a specific speed or anything. It just needs to respond when one of the drive axles moves. Yeah. I also have a little HMI, which stands for Human Machine Interface. This one isn't in the frame because it's standing on my desk and my camera doesn't have, it's just a cheap webcam with not that wide of a view. But for now we'll stick with the crane model, so this view should be more than enough. Should be sufficient, let's say it like that. Also on my desk next to me is my little controller. If you want to know how it looks like, you can Google S7-1500, which is the controller I'll be using, I'll be programming with. I can also show you a little picture in my programming software. I'll get to what that interface does in a moment. See, I'll open it up real quick, just so everyone can see what this guy looks like. It's somewhat along those lines. Obviously here it's more simplistic. Now, as I showed, this software is called TIA Portal. You cannot see it. This is, for me, it's a remote desktop. On the very left of the camera picture is a black square, which is my programming server that runs all of that stuff, because this program is quite hungry for power. Okay. In TIA Portal, in the left pane, you have basically all your machines you have connected. What you have connected, you can look at here. Sadly, I cannot zoom in most of the text because TIA Portal just won't let me do that. I will try to rearrange my Windows setup to make it bigger in the future, but yeah, with work and everything, I don't have much time, sadly. Here we see we have two things connected. This guy here on the right is the crane model, and we can also see here in the left list this the thing where my cursor is. This is the PLC, and if I open that, I have a lot of folders where I can put stuff into and have to put stuff into that it works. This is not the real project. I'll open it up in a moment, then I'll show closer what each thing does. I'll probably be streaming to around 10 o'clock. UTC should be, let's just call it Zurich time. I think it's UTC +1, if I remember correctly. Because then it's bedtime, because I have work tomorrow. Now I've opened up the real semester project. The other one was the one from last semester. I'll probably show that during the stream a few times, because I'll be taking some code from over there. Let's see. Now here in the real project we'll see that I can zoom this in, which would be very cool. Here is our network, how everything is connected. My programming server is over here, and the PLC has two things connected to it, the motor controller right here and the HMI here over the so-called Profinet, which is just an industrial Ethernet. It's basically it's based on the same thing that it's based on the same thing your computer uses if you plug it in with a cable to get internet. I know, very old school. And here on the top with the pink line is the crane model. It uses a different connection type. It's called Profibus, which is a different protocol that is based on something different. I don't want to get into detail of that because I think that's a bit beyond the scope. You can Google Profibus if you want to learn more about it. It's quite interesting, I think. But I think a lot. So let's put that thing into a good use, and for that I will hop back on my pedestal. See? Last time we started with the PLC, with just programming with just writing a program in the PLC to control the crane model. Because I like to do stuff step by step, and since the motor controller doesn't really do anything important besides turn a bit when the crane model moves, and the HMI is like the visual interface that builds on top of everything, I first need to be able to move the crane around. For that, I'll go into my PLC, and if I open it up here, you can see I have a hardware configuration. I already pre-made that because that took me 13 hours, and I don't want to torture anyone. They at least. Now here in my controller we have a few things. We have our variables. Everything that is connected here in the network has physical in and outputs that connect to motors, sensors, and basically everything that drives and sees stuff. Moves and senses stuff. That's a better description. And so we have to tell the controller what that is and what address it has. If anyone is familiar with computers, it's everything based in ones and zeros, and 8 and 1 bit is is either 1 or 0, and 8 of those bits make a byte. So everything in here is addressed in a byte and a bit. Like, for example, can I zoom the text in? No, I cannot, sadly. Sorry. Here is written I128.0. I stands for input. The 1 to 128 is the byte address, and the 0.0 is the bit inside that byte. 1 byte is 8 bits, so it goes from 0 to 7. This was already pre-made by the university I go to. So I did not have to do a lot, but I will in the future have to populate the table for the motor controller. So that'll be interesting because I have never done that actually. But enough of the intro, let's go into the program. Last time we stopped at the building block where we look how far we moved from our 0 point. The model, if I put it up on the screen here, I'll move over a bit and show it with my finger. The point where I showed is a little sensor, and that thing shows where the 0 point is. And from there we count up until we reach the top of the rail, which I've actually never tested that. I think it's somewhere about 140,000 steps or something. I could calculate that. In the documentation, the resolution of the encoder is known. But I'm not going to do it because I'm not really needing that. I just need to know the points of the storage spaces, which I'll find out in test, but I think I'll do that off stream in the end. Anyway, we have made a manual mode and an encoder block for every axis. We have an X, a Y, and a Z axis. For forwards backwards, which is X, up and down, which is Z, and Y, which is left and right, so out of the storage and into the storage. I know it's a bit weird, but the school wanted it built like that, so if the customer wants something, you have to do it. Now, I tested them last time a little bit. They actually count, but I had an idea where I can visualize it way better. There is a function called trace in here. I've not prepared that and I have not used it in a little bit. You guys can go away, I don't need you. Now I have made variables. I have not made variables, I just remember. This stuff, I'll make it a bit bigger, is basically getting written into nothing right now. So we'll, for testing purposes, we'll make some variables. But for this, we will need a way to store them. I'll hop on the pedestal for that. See, we have multiple options for blocks here. The organization blocks are just for the operating system. Certain block numbers get called when specific events happen, so you can error handle and stuff. Function blocks are like functions. You know from other programming languages, you can just define a block of code that does something, and you can reuse that with just calling its let's call it its group name. A function block is basically like that, and it has a memory attached to it, so it can remember between executions. Function, on the other hand, is stupid. It works the same. It's a collection of code that does something, and you can call it over and over again. But it doesn't remember anything between executions. Our hand mode is, if I remember correctly, our manual control is a function, because it doesn't need to remember anything. It just needs to look which button is pressed and drives the corresponding motor. Now what we need is a data block. Data blocks are literally, they store data. And I would like to have a data block that's called global. Because in other programming languages you have global variables. And here you have to directly store them into a data block that is globally accessible. Technically, every data block is globally accessible, but if you designate a certain one to be the one with the global variables, it makes the code much more readable. Now let's see. We have static variables only. There are no temporary variables in here because all of those variables are consistent through multiple program cycles. With an industrial controller, you have to think in program cycles. Like the program gets executed from top to bottom, left to right, and then it starts all over again, and that's a constant loop. And those variables are consistent through multiple of those cycles. If something is not consistent through multiple cycles, it's just a temporary variable. Okay, now what we want to do is they're just for testing purposes, I'll delete them later again. So this is encoder X axis, then we have encoder Y axis, and encoder Z axis. Nice and descriptive. Now I'm not sure what data type did I use again for these. I think it's a double integer. Yeah, it's a double integer. Double integer in Siemens is, I think, 32 bytes long. So it goes up to, what was it? I think about 2 million. Would need to look that up, don't know the detail. So we need to tell it it's a double integer. Int, the last one. And now we go back to our traces. And what I can do, I have a little table over here. If I select, I have the traces open now, and I can select the data block and just pull those guys in. And now we have them in here. Now I'll need to load them into the CPU because they actually don't get recorded in the TIA Portal software. They get recorded inside the PLC, and then that data gets sent to the controller. That data gets sent to my software. Yeah, that's it. And now I have a problem. I have not updated the software that is loaded in the PLC, and I have added a data block that now does not exist in the PLC. Let's oh no. Oh no. Oh no. Let's go offline again. Oh, now I can load it. Load my new data block into the PLC and see what happens. He is looking green and he's running. Now I should be able to get my traces in there. Very nice. Now here on the bottom, which one? The x-axis is red, the y-axis is blue, and the z-axis is green. Now I'm just gonna move the x-axis to demonstrate. I'll first have to drive it all the way back onto the sensor so that it zeroes itself out. And after that, I'll drive forward and we'll see what graph we get. Now let's switch to cam mode. See. Did it record? Oh no! I've done the stupid. Not activated. Whoops. Now it's running. I feel like I have missed something else. Not use these guys in a while. No, I have not forgotten that. You can set the max duration that it records, and I said already ticked the maximum, so that's good. Live again, delete what it not recorded, load, new, and observe. Let's see. Now, did it do anything? Stop. Go that 2 seconds. Oh, that's interesting. Oh no. Programming after a long work day. I have not put the variables into the program itself. I just have random variables in a data block. They aren't connected to the actual outputs. Whoops. Now I obviously need to load that stuff again. Stupid mistake, stupid mistake. Okay. I'll drive the thing back so we don't have to look at that much garbage data. Just before the sensor, and we'll load our tracer configuration and start recording. Ooh, that looks pretty nice. As you can see, if I zoom in, can I just... I can somewhat zoom in. It's okay. So, from what we can see, as soon as I started driving, it dropped at a constant rate. But it started at around 140,000. And then then it actually reached negative, and then we went on to the sensor. Like right here where that... Can I actually not zoom in? Dude, why are you doing that to me? How dare you? How dare you? Oh, no. Now, right here where that little spike is, I hope it's actually visible on the stream, but here is a little spike. That's where it hit the sensor, and I have in my program, as long as the sensor is active, the value stays at 0. So as soon as it left the sensor, which is right here, it started to go. Zoom out again. Again. Yes. It started to go up again. Yeah. Start to go up again, and now we are zeroed in, and this should work with all three of the axes because it's all the same data block, because I have written it once and copied it 3 times. Well, not copied it, I reused it 3 times. So that's pretty good. Now we shall delete them again because they actually take processing power, and these little controllers aren't really that powerful. You can somewhat equate them to, I think, 90s computers in terms of memory and power. And they are very expensive. The more powerful one that actually have somewhat decent stats for a computer. Let's say it like that. But it also doesn't really matter for what they are actually used. Okay, now we have a positioning system, we know where we are. So I'd like to show you something. I have a second software here that's called OFT2, and I'm using this for free because it is free to draw my little graphs. I'm drawing it mostly according to the graph set, GRAFCET standard. I think it's made by the French, because of course it is. And I have brought on my desktop my old semester project from last semester, because I can actually reuse some stuff from that. Here. This is the positioning. It looks quite complicated, but it should not be. Did I? Oh, no, I already edited last stream. Yeah, I made it a bit smaller. That little branch at the top wasn't needed. See. Now we start up here and go down. If it would let me zoom, nice. Hand, please. Nice. Okay. Yeah. First, we read in the variable from our HMI. That is basically, you can basically equate that to what the user chose, where he wants to go. And you write that in an internal variable that we control, because the user can change the variable on the HMI at any time, and I would rather not deal with that. That makes the program much more complicated. Now down here we have this double bar branch, which is called a parallel branch, because the program can choose the left and the right path to work on the left and on the right path simultaneously. We just focus on the left path because both of them are the same, just for different axes. I will have to copy that guy for a third time for the y-axis, because last semester I did not have to worry about that guy, because I could just move it in the end sensors and just drive until they were activated. I cannot do that anymore. Teacher doesn't let me. Way. Okay. These blocks are our states. That's where something happens, and the little plus signs here are our transitions. These are values that need to be need to be true for the program to advance to the next state. So I would kind of equate it to a state machine. Like you have a state, then a condition happens, then you go to another state. Like some video games NPCs are somewhat programmed like this. Obviously, it's a different field of how you program stuff. Industrial controllers, you always have to make your stuff fail-safe. Plus, you have to be aware that the user can turn off the machine at any time. So you have to account for that. I don't have to draw it in here, but basically every state also has an escape sequence that needs to be done when you pull the emergency button, basically. Because it would be bad if you just pull the emergency button and then nothing works anymore and you have to restart you have to power cycle the whole machine. That would be bad. The machines we have transport pallets around our building, and our building is like 1 kilometer long, so that's a lot of conveyors. And if you have to restart every controller along the way, because there are multiple of them, then you'd be busy for quite a few hours. Okay, anyway, we have here our branching instruction, and then we are here at this T-junction. This is not parallel. The English word doesn't come to me right now. It's just not parallel. The program can just choose one of those paths, so it can either go down or right. Now let's look at the conditions that need to be met. I'll zoom in a bit more. I think it makes it easier to read. We have an end position X and our actual position. The act position is I call it the actual position. I probably should rename it to current position. Anyway, it's the position where we are. Now, if the end position value is bigger than our actual position value, we need to move forward because our actual position needs to increase. The opposite is true if we need to go backwards. The end position is smaller than the actual position, so we know we need to decrease our actual position, and so we need to drive the motor backwards. In the crane model, these are just two binary, two Boolean outputs. A Boolean can only have two states, 1 and 0, and we have one output to tell the motor to drive forwards and one to tell to drive backwards. That means we only have one speed, but makes programming a whole lot easier. So let's say our end position is bigger than our actual position, and now this is true. So we advance to state 3. We turn on the output motor X plus. So we drive forward. And we'll drive forward until this condition down here is true. End position X equals actual position X. If both are equal, we know we have arrived. Now, I have written a little annotation here that says plus minus 2000 steps because the resolution of the encoder is so small that it'll never reach that this expression in itself will never be true. It will always over or undershoot by a little margin. So I'll program in a little tolerance for it to stop at. So let's say our end position is we need to stop at 10,000. Our end pos x variable is 10,000. That means our actual position will be somewhere between 8,000 to 12,000, which isn't a lot. I think, if I remember correctly, 2,000 steps are, I think, a millimeter or something along those lines. It's not much. It's so little that it doesn't matter, basically. We have at work, we also have that. It's I'm obviously living in a German-speaking country, so everything is in German. It's called Be- und Entladeabweichung. Be- und Entladeabweichung, which basically means load and unload offset, so loosely translated. And some machines can have it up to a few millimeters, but it's very tight if you have like 30-meter tall cranes and stuff that are only allowed to position in tolerances of about 20 millimeters or something. No, those are actually more precise. I think those are around 10. The older machines we have are around 20. Yeah. Anyway, it's not a lot for 30-meter tall, 80-meter long machine. And if both states have reached their, if both of these transitions are true, the parallel merger here will activate and pull everything into state 5, S5. And that just sets a variable that says inpos equals 1. So the variable inpos will equal 1, and 1 will be handled as we are in position by the program. Well, today I'd like to program some of that stuff so we can tell our little crane to go somewhere. It'll be quite in how we tell it to go will be a little rudimentary because we don't have the visual visual machine interface yet, but I'll make it work. That's what an engineer does, baby. For that, we will make a new block, new building blocks. And since it will have to remember variables across multiple program cycles, like our actual position and end position and stuff, we will have to take a function block. And I'll call you, what did I call you in my old project actually? Positionierung. Okay, let's just translate that. It will be function block positioning. I have a feeling I have misspelled that. No matter if I misspelled it, I can always correct that later. Oh, and we want to go offline again. We don't need to be connected, actively connected to the PLC. And what I like to do here, the title, just paste. I'll just paste it in. That's just how I do stuff. In visual style, there is a lot of possibilities. Some people like to program certain ways, like with every programming language. I hope I offended nobody by calling this programming, because I think it's closer to scripting than actual programming, but I digress. Now, here in this box up here, we need to define our inputs and outputs. As I said, this is a block that represents multiple actions, so we need to give it stuff and we will get stuff out for that. And we need to define that in this little interface here. Now let's go back over what do we need. we need an input that is our God, English does not. Dictionary, help me. Target position. Oh, that works. We need a variable that represents our target position. The target position. We need a. No. It will be an. Let's just call it a double integer. Let's just make it big. I can always make it smaller. Double integer target position. Yes. I'll only program it to accept one set of coordinates because I can copy paste that for every axis in the end, which will be much more efficient in terms of writing code. Now, you know what? I can't scale the text anyway, so I'll put guys. I think OFT doesn't like it. Nope. Yep, doesn't like it, but it works. Okay. Actually can delete that stuff. I don't need that anymore. That was from the old program. That did not work actually, which made me not fail, but the deduction in the grade wasn't very nice. Yeah. Memories. Okay. Now we have our target position, and we need an input that's also double integer. That is our current position. I'll also rename them over here to make it consistent. Can I please rename you? Because I'll need to hand that stuff in as my documentation, and the teacher would be confused if I did not have that. Yeah. I just had an idea. Ooh, that would make it way more efficient. Ooh. I'll not make schematics of the whole, basically how the whole program does, just of how does the function blocks do stuff. That'll make it a whole lot smaller, a whole lot easier to read too. Come on. Because this is basically all that happens. The others are just copies of the same code at that point. And if I just write in the comment, yeah, this will be repeated for each axis, I think that should be enough. We'll see. Let's roll with it for now. Can always expand it. Okay. Now obviously need to change numbers around, and this should actually be a different symbol. There are different boxes for different functions, and the start box should always look like this. Why are you connected down here? Why are you doing that? What are you? Why are you? Okay. You're connected? No. Now it is connected. Very good. Yeah, now the start block looks like this, and step 2 needs to look like that. It's always number left to top to bottom, left to right. And this is now step 4. In the old project I did some stuff with nested nested states, which looked hideous in the end, but it worked. I don't think the teacher enjoyed reading my documentation, but yeah. Wider, yeah. Target position smaller than current position, target position bigger than current position. That's good. Let's do that and make you go there again. Please do it. Nice, nice, nice. That's how we like it. Cursor. Okay, now we have 2 input variables that are being written. Oh, I forgot to change that. Yeah, there's a lot of variable changing. You copied the wrong one. The list of positions were the list of positions, I thought about it. I wasn't sure last stream how I would do it, but now I am pretty sure I'll do it with an array. I'll show how I do that when I get there. It's, as with everything in TIA Portal, it's very abstracted from the hardware, I say. So it isn't, no, I'll say different. It isn't that abstracted from the hardware, but it is very visual. We'll see when we get there. Now, first, yeah, we have our target position, we have our current position, and now we need to have some outputs. We have motor. Since we don't specify the axis in here, because that will be specified by which output I'll connect, I just call them motor plus and motor minus for forwards and backwards. And if I put that in, I can see more. Good. And now we need to comment them. This is our position. We need to reach and position where are. No, position. Nice. And this will be our motor forward and motor backward. It's forwards and backwards. Good now. Now let's think. Do we need internal variables? I don't think so. But we also need, I'll put that in the input variable because I want to be able to change that dynamically. If I put the stopping tolerance in the internal variables, the static or constant variables, I could not change it from outside of the block. But I will probably need to change that when I actually have the automatic moving of blocks in programmed. Let's see. How could it? Yeah, just call it stopping tolerance. This will be an integer, and normal integer, because that goes up to 32k and we don't need that high of a number. integer stopping tolerance. I think that's pretty self-explanatory. Okay. Then we also will need to set the variable. This will be a global variable because we will need to the next block, the block that comes next in the automatic mode will need to be able to read that. So we will need to make it global. So we'll have to put it in the output x in pos. The x is how I'm writing variables is according to the Hungarian notation. You just prefix your variable with a letter that stands for the data type the variable represents. This is we reached end position. Very good. Okay. Now we can start to write our code. Wouldn't be too much. We will need, what do we need? We'll need two. I think we'll need two networks. For structuring inside the block, I can subdivide the block into networks that each do a different function. Like one, I'll do it like one of them will will have all the conditions for the forward motor, and one will have all the conditions for driving the motor backwards. It's the same motor. Key. So I just like to start with the outputs. I know this one will be for driving forwards, and this one will be for driving backwards. Yo. What I would like to do is let's just do the motors first. So he should be running. Let's make you big. Let's make you small, and let's make the blocks bigger so everyone's able to read that. I think 200 is far better. Yes. And take out our little library of stuff we can add in here. Now, for the motor to be able to go forwards, what did we say? The target position needs to be greater than the current position. So we have a comparator here, and we need this guy. I'm always confused which one I need to use, so that's on me. Oh, I also need to set the data types. Double integer, double integer, and integer. Very nice. But now we have a little problem. Our target... Oh no, we don't have that problem. Never mind. Our target position is bigger than our current position. Oh, it's a double integer. Yeah, I need to tell that guy what I input into him. Now I just copy that down here and change that icon to the opposite. And this would already work. But for safety, I'll put in a little blocker. When you have, let's just equate that to a physical, let's just picture the physics here. What happens if you try to drive a motor forwards and backwards at the same time? Well, with big motors like we have at work, there would be a short circuit and the breaker would trip. These guys, I already know that because I had that problem last semester. They just don't do shit. They drive nowhere. So I'll always like to put, no matter how big the motor is, I already put a little failsafe in here. Now, the failsafe basically consists, I check if the other direction is already on. And if it is already on, I'll not drive, I'll lock the other direction, that it cannot be activated. Now there is a little programming convention that kinda plays me dirty here. And the fact is, xmod plus and motor plus, motor minus are both outputs. It is bad practice to to use outputs as inputs. You can do that, but it's generally not a good thing to do. So I'll do something a little bit weird here. I'll make an internal variable that represents my motors. Because this variable I can read in again. And I'll just call that guy xmod plus status and xmod minus status. Remember, the x just stands for the data type. X is a boolean, so either a 1 or a 0. Motor forwards status. Now what I like to do is, if there's a status, I'll tell you what that status does. Like this one is 1 equals active, so the output is active. And same here, motor backwards status. So if the status, my status variable is 1, the output that it shows the status of is active. Now what I can do, I can make a little branch here and put an output block and put my status guy in here. And now my status guy can also be in here because an internal variable I can write and read in as often as I want. Minus goes there, and I also need to write minus. Yep. Let's put output block here and this guy. Nice. Now the funny thing is, I said that the program will be, I'll make it a bit smaller so it fits on the screen. The program will be looked at by the operating system from top to bottom, left to right. So let's say both directions would want to go at the same time. The program would go, oh, okay, you are true. Motor minus is not active, so we activate motor plus, motor forwards. And then the motor backwards will always fail at this AND gate because motor plus is already active. Even if this condition is true, it'll always fail because this condition here will be looked at first come, first serve. So when in doubt, it always drives forward. But that shouldn't be a problem, really, because this stage shouldn't actually happen. I just like to do it for safety. Okay. Now Now we have exactly this. But our end condition isn't met yet. Because right now, let's say we drive forwards and we overshoot. Then this one becomes false and this one becomes true. So this one deactivates and then this one will activate. Because this one is deactivated, so it will start to oscillate around our target position. And we don't want that. So what I'll do is I'll put in here a little something that I think most people will know as a flip-flop. Here in TIA Portal we call it an SR block. It's a description of what it does. It sets and resets. If you have a positive on the input, it'll set, and if you have one on the R input, it'll reset, so it'll go to 0. The one that is seen here on the R, there's also another version that has the one, if I put that down here, that has the one on the S. A little bit. Can I just zoom in like that? Yes, I can. Here, one is on R, and on this guy, one is on S. That's the dominant one. If both inputs are on, this one will set, so it will turn to 1, and if here both inputs are 1, it will reset, so it stays at 0. Most of the time you need the reset, the one that prefers to reset itself, because in general you want to have the off state also as a 0 in this kind. Now I can actually move the stuff a bit around because we don't need this AND gate anymore. I can just put in here, since I will need multiple inputs here, I can put this guy down here. And now we actually have the same function as before. If this one is true, it'll send a 1 to the reset, and since the reset is dominant, is preferred, it will stay off. And we can also do another neat trick. You need to declare a variable here in the static variables for the SR to write its state to. It needs to remember its own state, and that so it will put it into a variable. And that's a little trick. I just put the output variable as the status variable of the SR, which makes the program a bit more compact, which I think is kind of important if you program with these blocks, because the program will get really large really quick. Now I'll just mirror the same thing down here. See, SR output as the status, and yeah, here I'll put an OR, and the AND can go. Now I'm thinking right now. I will need to represent this condition in the program somehow. I have an idea. We just get one number as input. That is our tolerance. And I'm thinking of, that's why I made this guy here. Here we calculate our total. Calculate total stopping. tolerance. I'll probably rename that stuff to way more better names, but I'm bad at naming stuff from in the moment. Now, what I want to do is let's say this variable will be 2000. So what I'll equate that to is I'll take our target position as the middle point, and then I'll add half of the stopping tolerance to the top. That will be our max tolerance, and then I'll also subtract from our end position to make it our minimum of tolerance. Now let's get some math going. I don't know, I'm getting slower. Brain does not want to work at 8 in the evening. Okay. We take an addition block and a subtraction block. And we want to feed you a double integer because our input, our current position and our target position will be double integers. So I would rather convert everything up into double integers than convert everything down into integers, because if the target position or the current position are at the very end of the rail, the values will probably overflow a normal integer. It'll get too big for the integer to hold it. Okay, now let's take away tooltip. We take target position for this and target position for this. Now our stopping tolerance is an integer, and I would like to keep it that way because that will take less memory in the HMI itself, and those guys are also quite limited. So what I'll do is there is a block that can help me with that. That's called convert. Convert u from an integer to a double integer. And you will write yourself into, I'll just take your name. And now that's the funny thing with the Hungarian notation. I can just add d to the front, and now it's dn for double integer. Don't ask me why n is the English word missing. The character for integers, it just is. And no, come on, let me do it. Double integer stopping tolerance and integer stopping tolerance. And we can pull that then down here. And now the add will take the target position and add the stopping tolerance to it. The subtraction will take the target position and subtract that. I'll just make all of these temporary variables because they will get recalculated every, it's no big deal if they get recalculated every program cycle. How do I call you? I think you will be double integer tolerance max en tolerance min. Come on, go there. So now Yes. And now we can replace. Now we cannot replace. This one still needs to be the same, but we can insert that into our reset condition, integrate in our reset condition. Because we need to stop if. There's not really an if statement in with these blocks. I will need a comparator. God, now I'll get confused by these operators again. I'll guarantee that will happen. We drive forward and we want to stop inside of these values. Thinking. Current position. We obviously need the current position. If the current position is, oh yeah. The current position is smaller. Yes. If the current position is smaller than the maximum tolerance and yes, I think that should work. And it is bigger than the minimum tolerance, we need to stop. Current position is smaller than max, so we have not overshot. Current position is bigger than min, so we have not undershot. I think that should work. And the same reset condition needs to apply down here. Yes. And it will get blocked by the opposite status. I think that looks quite good. Let's save that. TIA Portal doesn't save by itself, sadly. And we have covered, oh, we still need to set this variable. Network and how do we call that? Output. How do we call that? As I said, I'm bad at giving names. Let's just make the program first. I can name that thing later. In any case, I will need to set in pos to true if this condition is met. Yes. And I'll add something else. The motor statuses need to be off, because I don't want the program to continue when the motor is still running. Just as a failsafe. Because these motors are on spindles, so they stop on a dime, but for safety I'll still do it. Yes, if these are 0, these are 0, then it will go. Very good. Then it will set x in pos to true, and this will trigger This should then trigger the next block in line, which would be the taking of one of the blocks out of the storage. It just pulled up my OBS. Hello, there's a viewer, hello. Sorry for not noticing. I'll blend in my little setup here on the top right. We are automating the red thing, which is a little model of a storage area with a crane that will be able to move automatically and place aluminum blocks in and out of the storage. That's the basic gist of it. Okay. Now we finish this block and need to recollect myself. I'll save this guy and save as. Why are you putting the file name in here? How dare you? Graph set positioning. Save. Okay. Now it's this. And we'll need to start working on the next one. I'll show the overview real quick. It's the automatic mode. What we basically have done right now, let me zoom in please. What we basically have done is we programmed, cannot select, we programmed this one. Step 2. Step 1 is just our wait action, wait for a new input from the user. Now we have positioned, so we already did two things at once, because positioning is I really can't decide between cursor and hand. We already did position 2 and 3, because we will need to position twice, once at the position where we need to take a block and one where we have to put the block in the storage. Now we need to load the block, which means we'll have to move the y-axis. I'll close down you. I will not need you for now. We will make a new block. Or do we make the block first? No, we don't do the block first. We'll need to plan the block first. One. This is OFT2. I'll use it to draw my diagrams according to the GraphSet standard, which is written GRAFCET. I think it's made by the French. I just learned it first, so I'm using it. Other people draw it differently. Okay, we have our first state, which is our initial state, and that one doesn't need a block. Second state will need the block, but we will need a transition between them. Okay, make this a bit spaced, just like that. Yeah, very nice. Okay, our initial condition will be, is x in pos true? Is it 1? First thing we check, because if we are not in position, we cannot start. You must be number 2. Then what we will do is we will we will just need to drive it forward. So can we just... I'm really annoyed that I'm not allowed to do it just with the sensor, because it's really just a forward and a backward position. But I have to do it with the encoders, and that annoys me. Okay, so I need to load my forward position. Loading in TIA Portal is done with a move command. You can picture that as basically as a copy command. I'll have one variable and I copy my value into my work variable. Move, let's call this, it's just pseudo name now, forward position into forward position into, I'll take a double integer because these will get quite large. And move this into double integer forward position forward y. Yeah, let's run with that. And I'll adjust the size of the block later. Now we need more blocks, more transitions, more of everything. See. You'll notice when I'm thinking hard because I talk less. That's the turtle in me. Can't do multiple stuff at once. Okay. Now we have moved our forward position into our working variable. So we need to compare that variable to our current position. So we compare dn pos forward y to it's basically the same we did before. Can I just copy paste that? I probably can. Yeah, I can just copy paste that. Let's be lazy. Half of the stuff did not copy. Very good. Aww. Delete that. Come on. Please program. Cooperate. That looks better. Yeah, that looks better. Way better. Oops. Get ourselves over there again and move you in position. Okay, now let's change the variables around. We have our dn pos forward y that we compare to our current position. I should probably copy paste that. That goes way faster. Yes, we basically do the same as we did before. I'm just thinking. technically, I will be able to reuse our positioning block. Ooh, I was just thinking to use the positioning block for like driving forwards, backwards, up and down, like the X and Z axis. But actually, the Y axis isn't different. If I have to move it with the encoder, it's not any different to the X and the Z. So I can just reuse the positioning block. That's very nice. That simplifies the graph a lot. So that means I don't need this stuff. Let's take a look back. Yes, I just have the target position. Ooh. Brain going brrr. In pos? Yes, I'm in pos. I need to check it. I still need to check if I'm in position. I always need to do that when loading or unloading. And I will not need to move this one because I can just directly connect that to my positioning block. So I'll just basically we call our FB function block positioning. Yes, exactly. I'll call that, then that guy runs. Oh, but now I have a problem. If I want to reuse him like that, I am not allowed. No, I can. I still need this variable. Okay. I'm skipping my thoughts here. Okay. What I just thought of, I can't use this variable. If I want to use this block for all three axes, I cannot use this variable. But that's wrong. I can use this variable because what I neglected is this is just the variable that's internal inside this function block. To what I write it, what I put onto the block here, like it'll look like this block here, and here I can just put anything. So I'll just make a different variable where I put that in position in. So I can just make a new, if this guy finishes, he'll just write himself. He'll just write in this in position variable will be written as a, let's just call it loaded variable. Yes. Yes. Exactly. And with this, I can escape the loading. That was a lot simpler than I anticipated. I feel smart right now. Okay. I'll just check for this variable, call, if it's true, I'll call my block and he will set the next one. Yes. Perfect. I can still make that function block just to organize the program, because those blocks can not only be used to encapsulate stuff you use multiple times, they can also be used to organize your program. Let's make a small detour. Where is it? Here it is. This is from my last semester project. I just drew this to visualize for myself how the program will be structured. You have your OB1, your main program that gets called every program cycle. Attached to him is our global variables, and inside this OB1 block will be one function, that is the manual mode. Everything's in German, because obviously my school is German, so I had to do it in German. Sorry about that. This is the manual. This is just a normal function because it doesn't need to remember anything. And here we have our whole automatic. And as you can see, inside the automatic there are a lot more of those blocks. So these two aren't really necessary. I could have just left this one, just not created this one and put everything. What did I do? Oh. And put all of these blocks inside my OB1. But that looks ugly as hell. So I just encapsulate them inside this block. As I said, this guy did not work mostly. The position calculation was quite weird. I actually don't know what's wrong with it, but yeah. Let's hope this one works better, or works at all. We'll see. So let's still make I don't know, right there. Let's just make a function. I'll just make a function block. You can always switch them later if you want to. You just make, if you made a function block and you want to make a function out of it, you just create the FC and then copy everything you had in your FB into your FC. Yeah. It's not a big deal. Let's call this FB loading. Yes, and for consistency, write that in here. And now we program all of that. We obviously need our inputs again, and our inputs will be X in position. Are we in position? We need that. I really need to give that guy a different name. Oh, something for later. Programming depth, let's go. And inside here we want to call our positioning. And now the program asks us, every function block needs to have a data block attached to it. So we can either make one that's standalone, or we can embed the function block of our positioning FB into the data block of our loading FB. I'll show you how that looks like. I don't want the word instance back there, go away. And now we see in the static variables, something appeared. And if we open that, we see the whole in and outputs, all of the in and outputs of our positioning function block. So he is now embedded inside the data block of our loading function block. That's the whole nested thing that I also had here, like the little data blocks, these guys here, were all embedded into this guy. I hope that makes sense. Yeah. Now we obviously need to populate these, so we also need to pass them through to the outside of our loading function block. So we need di target. I just call them the exact same thing because they are the exact same thing. Di current position. I was writing position. Sounds poetic. I'll show myself out. Stopping tolerance. And on the output, we obviously need x mod motor plus on and motor minus. And now we need to set the data type because they don't get set automatically, sadly. And an integer. Wonderful. And now we just pull them in here. Come on. Go in there. And the outputs go here. Nice. But now we already have most of the work done. One problem remains though. Over here, we have our starting condition. In-pos must be 1. Our positioning doesn't have an input to tell it to start positioning. That's a bit of a problem because this FB loading I probably will be calling, I'll just call that, and as soon as I call that, it'll start to get executed from the top. So it'll start from top and just read, oh, there is a function block positioning, I'll just start that. That's kind of bad. So as soon as we call that, it'll start to move. Even if the in position variable is set to 0. I would like to edit this, and for the start conditions, I'll add an and a new input variable up here. That's just a boolean, 1 and 0. Start position. And you know what? I don't need start position. I just call start. And I want to rename my in-pos position to finished. I think that's way better, so it doesn't share a name with our transition variables between loading and driving to a new storage spot. So I'll also need to rename this over here. You are X finished now. You'll set that to 1. And we need to have a new position. What are you doing? Don't do that. I need to redo these conditions. You go away. You go up. And let's insert. Hey, what are you? This program sometimes, I like it. I cannot complain because it's free, but yeah. Okay, let's draw the line again, put you here and delete you so I can make a new state. No, I can make a new transition. I'm confusing myself. Yes, because I'm doing it wrong. That's why I'm confusing myself. I don't need to add anything. I just need to edit the start condition in here. So I'll move this over a bit so I have more space. That's not how you make a line break. This, oh, shift enter it is. And x start equals 1. No, it'll still put it at the end? Okay. All one line it is. That's gonna be a long condition. And now let's copy you and put you at the end of here. So now the target position, I'll just show it on this one. The target position needs to be greater than the current position and x start needs to be 1 for it to start moving. So, and x start go here and x start also go down here. Good. Save. Haven't done that in a while. Now we see here everything is red because we changed in and outputs. Now we refresh that. Yes, please. We also need to refresh the data block instance, so nothing is red anymore. And we have our start input here, and we can take our in position variable and just plug that in there. As an output, we also need our loaded variable, and we can plug that right in there. Noise. But that can't be any of everything. That was too easy. That was way too, because it was way too easy. I forgot half of the stuff we need to do. Because now we have just extended the fork, the thing that takes the blocks. I'll just call the fork. Now we have just extended the fork. We have not lifted anything up yet. So we want to do that. Not here though, just save that. Yes, we want to do that here. Oh, I have not saved you yet? That's bad. G underscore loading. G just stands for graph set. That's my file organization. Okay. Oh, we can still use the x loaded, but we cannot set that here. We'll need to set that way at the bottom. I'll just delete it for now. Okay, now we have extended the fork. Now we need to lift the fork. So that means we will need to call the positioning block again. This time we still need an outputter because we will need to know when the positioning of the y-axis stopped. Let's just take, should I take a temporary? I'll take a temporary because these ones don't need to be saved beyond this function block. That means this is x in pos y. So the y-axis is in position. Very good. So we can detect that like this. Yes, we just call this guy again. That's what you want in programming, just reuse everything. But now I have an idea. The z-axis is the one that lifts or lowers. So, and the fork is now in the storage. So we need to lift it a certain amount, but this amount will always be the same. So for the target position, we can take an addition, which we can't plug in directly. Oh, damn, TIA portal, why? Then let's put it up here. I'll connect that in a moment. So what we do is we take our current position and we add an offset to it. Will that work? If it gets, yeah, it will be executed. I just had a thought. This block will take multiple program cycles to complete. And I just use the input, the input y variables in the temp is a temporary variable, so it gets forgotten after one program cycle. So I need to make it static, because static variables are remembered for multiple cycles. Okay, and that also puts this add block into a bit of a predicament, because I want to take my current position and add my, let's call it the lifting offset to it, so I get a new target position. But if I do that every program cycle, I will never reach that target position, because my current position is updating, and the lifting offset will get added to it again, so it will just chase itself forever. So I need to have that add block, that addition, only be done once. Well, that was a thought. Thinking, how can I do that? How can I only execute you once without bloating it too much? You can do everything with a lot of stuff, but it's art to do it in small. I have an idea. Every block, I don't know if it's noticeable, but every block has an enable pin. That's basically if on that enable pin you put a 1, a true, then the whole block will be executed. If there is a 0 on the enable pin, then the block will be ignored and not executed. That could work. So that means I'll need a condition here I'll make it a bit bigger, makes it easier to read. Just working on that. I'll need a condition here that is true only for one program cycle. Technically, I have an idea, but I don't know if that works because of the cyclic nature of the program. Where is it? Is it under math? There is a counter. Oh no, here. It has its own folder. Countdown. Yes, you need a little. He is basically a little function block disguised as a program block, basically. Now, what do I call you? I see you're a counter. I call it first cycle because he needs to detect when we are on our very first cycle in this block. Okay. So you would obviously, which one is the input? I think is it the LD or the PV? Well, let's find out. TIA Portal has a built-in help system where we can look up stuff. If I highlight something and press F1 on my keyboard, it just opens it on the right page. Here is everything. Every program block available has one entry in here that tells you exactly what input does what and the description what the function block itself does and what the program block itself does. And here we have a little table and we see PV is value. It's in German, I need to translate that. It's the value that the output CV will be set if the input LD is 1. What is LD? LD is the load input. I think that's the one. Oh no, that's just a Boolean. Oh, and CV is the current. CV is current value. And PV would then mean, if V stands for value, what would P mean? Program value? Okay. Yes, it's probably the program value because that's the input. So PV needs to be 1. Like that, yes. CTD stands for count down, so he will count down from 1 to 0. Oops. From 1 to 0. CD, what's CD? It's the counting input. Do I need, where do I need to put my value now? I'll need to read that real quick. Okay. In the description up here, it says, with the instruction count down, you count the value on the output CV down. If the signal on CD switches from 0 to 1, the output CV, if the signal on CD switches from 0 to 1, the output CV will be lowered by 1. The number... Hello! How you doing? My brain's smoking. The value will be lowered if a positive signal will be lowered when a positive signal is recognized until he reaches the lower end of the data type. After that, he just stops. Oh, that's when he underflows. So that's an error. That would be an error at that point. So okay. But when does Q get set? Output. Oh, that's just the status. So Q doesn't really do much. Oh no, wait. No, he does something. The output Q will have 1 as long as the current counter value is smaller or equal to 0. That's actually really neat. So Q will be 1 if we reach 0. That's perfect. No, that's not perfect. Ah, shit. No, that doesn't work. No. No, that does work. I just need to invert it. Yes! Yes, that works. That works. I just look. Yes, I just look in on if my y position, if my y-axis is in position, and if y is in position, it gets set to 1. If he detects a switch from a positive signal on CD, he counts down by 1. And so this output will switch from 0 to 1, but because it is inverted, it will switch from 1 to 0. Now, yes, that means at the moment, because this variable also starts the lifting process, at the moment this positioning block gets activated, this value here is frozen in time until the loading FB is called anew. Well, that was a long sentence. Oh God. I need to drink something on that. Oh God. Okay. Let's see. Let's make some variables. This one needs to be static too, because it will need to be kept through multiple. Oh no, wait. Inside the positioning block, it is already static. No, it's just an input. Just an input. Yeah, then I need to make it static on this side. So he remembers it. It doesn't get lost after just one program cycle. Okay, so let's call you double integer. Names again. Yep. You are not a countdown block. You are a double integer. Now let's give you a real name. You're a double integer position. Let's just call it overlift. Because in German it's called something like that is called an Überhub, which literally translates to overlift. I don't know if that's a good idea, but I think it's funny. You go here and you go on the target. Yes, 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 yes. And the value I need here will be supplied as a. I think I'll also take that as an integer because it isn't that big and saves some memory. Integer overlift. Let's go. Okay. Oh yeah, I need to convert that obviously. I'm basically trading memory space for program speed, but my program isn't that heavy on the CPU, so I can afford it. I have the spending pants. Sadly, one problem with TIA-Portal is if it isn't a Boolean output, like an output that just has 1 and 0, you can't connect it to anything else. I can't draw a line and connect that. Bad design. Don't like. Me no likey. Okay, let's make a temporary variable for that one. Because this can be recalculated, doesn't matter. Yeah, it's just di overlift because this is the double integer version of it. This. If you have any question, just post them in the chat. I'm happy to answer anything I have explained badly. And now I need to put the double integer overlift into my addition. And that basically completes that. I'm happy with that. I just need to change this one. Now I've lifted the block. And now I need to pull the fork back out. Let's see how we can do that. I probably need to represent this whole shebang in my diagram, but I'll edit that later because I would like to move forward a bit. I want to go to testing at some point because I think that's a bit more That will be a nice break from just looking at blocks. At me pulling blocks around. And for pulling back, we just need to call the function block positioning again. So, oh, I need to edit this guy. You do have a different name now. This is X in pos Y. Okay. And go back to here. So, okay. And this guy, when he finishes, will set a transition variable, so we can transition to our state 4 and call our next position. So we want, how do we want to call that? We have lifted now, x lifted. Let's just not overcomplicate that. And this will be a static one too, x lifted. I'll need to add comments to everything later, but I'm already tired and I'm not feeling like it. Okay. We just copy this guy and change? Yeah, and change the variables again. There is one problem though. I'll address that later. I'll address later what that problem is. But I will need to solve it. And this position, I think, I need to add another variable in the input for that, because I will need one forward variable and one backward variable for the positions. So this will be target pos for let's just go with the naming scheme of the Mosers. This is target pos plus, so target position plus, which symbolizes forward in this program. Okay. Nice thing is it renames the variables, it renamed them up here. But we want to have, yeah, this time, yeah, we should switch our target position. And now we can set our output position. Hey, something's wrong here. Something's wrong, something's wrong. Oh, I'm stupid. The n overlift is not an output. That must be an input. Whoops. Screwing up my whole program. Well, I would have noticed it when I pulled in the block itself, so not too bad. But now I have, oh yeah, I already made that. Now we set x loaded to 1 and that finishes it. Yeah, he'll set that to 1. And with that, we have finished our sequence and are done. Woo! Interesting. I'm always amazed when I finish a block and look at it again, like logic. Okay. I think we can actually test that with some test values. Now when I pull, this is my main program, the OB1 that gets called every cycle. So what I want to do now is pull in my loading function block. Now we need to create the data block for it, because now it gets its own instance is called. Okay, and now here is a new one that has appeared. I'll probably group the encoders into one function block at some point, because those three data blocks here are just for they're just used to read out the encoders are really bugging me. They look ugly as hell. Okay, now let's see. We have to. Oh no, we can. Oh, that's a bummer. We cannot test it. Oh. Because of that other problem I mentioned. Now, this variable here, I'll zoom in a bit so it's much better readable. Let's go to 100%, so that should be readable. This is motor plus. And this down here is also motor plus. And this down here is also motor plus. So we use the same variable, we write into the same variable 3 times. And the program will be looked at from top to bottom. So let's say this variable here is 0. So the program comes. Oh, motor plus is 0. Okay. So it sets it to 0. Now in this block here, it is 1. So it sets it to 1. All good. Still works. Now, here it is 0. So it sets it back to 0. So nothing moves. And that's where the problem lies now. But there's a fairly easy fix for that. I just need to give every one of these outputs. I need to basically split this one variable into 3. And then in the end, I'll need to combine them again. I'll zoom out a bit because that makes it a bit easier for me. So I'll just make some static variable. And there is a really neat thing in here you can do. You can make something that's called a struct. Structs exist in other programming languages as far as I know. Here they act basically as folders for your variables. So if I make, I just call it motor plus, and I select as data type struct. And now I can put variables in here. So now I can have x mod plus for the extension. Let's call it just extend. X mod plus for extending the fork, X mod plus for lifting the fork, and X mod plus for retracting the fork. Now I'll put them here. I will need to do that 2 more times because we have 3 variables at our. No, I need to do that 1 more time because the the x mod minus is also like that. it suffers from the same problem. But now we see we have xmod retract here, xmod lift here, and xmod extend here, which are three different variables. And since I made the struct, I can just make a copy of it. If I can paste. Yes, I can paste. And I can just call you motor minus. And now I just need to change the names in here, and we have a whole new set of variables to use for the negative, for driving backwards. Extend, lift, and retract. Now we still only have one output variable per direction, so we need to combine those three back into one. How do we do that? We make a network and we put in an OR. Where an AND is true. Where did it go? Where did you go? Come on. So an AND is true on the is a 1 on the output if every input is a 1. An OR is true on the output if one or multiple, if any one of the inputs is true, is a 1. So we just take our real output, put it here, and then we take our three struct variables and put them on here. And with this little star, I can make one more slot. And this combines those three into the motor plus thingy. Oh, I just realized something. I just finished this one real quick, and then I'll jump to my next mistake. Because of course I did another one. No programming without mistakes. Let's just pull it in. Oh, I need to rename struct to minus as well. Okay, and everything's in. Nice. Okay. Now I just noticed another problem. An oversight on my part. This block and this block drive the y-axis. But this block here in the middle needs to drive the z-axis, the z-axis. I only have output for one motor, so I need to add more outputs. And motor. I just want to call them Y and Z because that makes it very specific, and I want to make these blocks generalized for a general purpose. So I'll just call them mod plus horizontal because it drives in the horizontal direction. And the other twos will be obviously called vertical. So many things to keep in mind. Vertical. Okay. Yeah. That means we don't need the lift one in our struct anymore. Oh. Oh god, I put a struct inside a struct. Oh god, no. I don't like that. No nested structs, please. Can I just... Oh no. Oh, now it worked. Okay. Just rename this one. Oh, why can I? Why did I make two? I am confusion. Anyway, we can delete our lift variables again because we won't need them anymore. Let's delete these guys as well. These ones are now confused. Let's reattach them. Very good. Okay. And here we need to attach we can attach the verticals directly because they are only written to once. Yes, 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 yes. That is good. That is good. I am happy with that. Let's save. And now we need to refresh you. Perfect. Do we need to refresh you as well? No, we do not. Nice, he did it by himself. Okay. Now, target position plus target position minus the target position for the lifting, for the vertical one, will be calculated from the current position, so I don't need an input for that. Yes, okay, that's good, that's good. So let's take our encoders, well, not the encoders themselves, because we have internal variables for them. We have decoupled that from the physicals, for physical ones. So our y-axis current position. Now, I do need another input because to calculate the overlift offset, I need the current value of the vertical axis. Let's see. Let's add that. We have current position. Let's shorten that. Current pos horizontal. I need to think of an abbreviation for horizontal. That's a long one. And now we also have an input for the vertical one, and that vertical one needs to go all the way in here. This is overlift, and the vertical one. Target current position. Current position vertical, current position horizontal, and current position horizontal. Good. We'll get there at some point. We can test that. A few years. I'll not take that long. So now our horizontal axis is obviously our y axis, and the vertical axis will be the z axis. And here, these are our motors. These are the physical outputs to the motors. So here in this block, we suffer the exact same issue we had before. So I'll need to make a new network with, I think, 6. Yes, 6. 6 outputs. 2, 3, 4, 5, 6, and let's structure them below each other. Okay. Put them like that. I'll probably pack that. In the end, I will need to make a function that does the thing that this network 6 does now, but for testing it's okay. Can I do that? Oh, cannot select multiple and add the ORs to all of them. Need to do it one by one. Now let's grab. I can split my view, but not into the same. Oh, that doesn't work. I cannot show the same block on the left and the right. They are always different, so. TIA Portal, why are you complicated? Why are you doing that? How dare you? I was right, just right. It's 128.0 through 128.5. They are continuous. So 128.0 should, to specify input 128.0. Nice, that works. Input 128.1. Input 128.2, input 128.3, input 128.4, and input 128.5. Very nice. Now we just need to define some variables to segregate all of this and to separate all of this. Separate is the wrong word here. Separate these. You can make temporary variables in here. You can't make statics in the OB1. I'll just use that for now as a placeholder. As I said, this will probably all move into a function at some point. So this is x manual mod plus. And I'll need to copy that 5 times. 2, 3, 4, 5, 6. Yep. This is x minus, this is y plus, this is y minus, this is z plus, and this is z minus. Populate that. Plus, minus, plus, minus, plus, and minus. And let's put it down here too. Plus, minus, plus, minus, plus, minus. Okay. And now let's do the same thing. You know what? I feel the urge. Manual motor. I feel the urge to make a struct. Now I need to assign them again. Aww. TIA Portal can rename variables if you move them around here in the in-output interface, but it's a bit limited. And I like my organization. Just good. And now we can make, let's just call that automatic. Let's give it a little bit more specific of a name. Loading motor, because it's from the function block loading. Copy. Yeah, no, I'll just write it here. X loading mod X plus, copy that through 2, 3, 4, 5, 6. X minus y plus minus z plus and z minus. Let's attach that. We won't need all of them, we just need the y for horizontal. A bit too many there. Mod minus horizontal, mod plus vertical, and the mod minus vertical. I'll just attach all of them, it doesn't hurt. It doesn't do anything, but it doesn't hurt as well. Less confusion for me. Okay. Okay. Very nice. Okay, this should work. Now, problem is we don't have our visual human interface now, so we'll have to write our values manually. I'll just force the in position variable to be on all the time, so he starts he just starts himself. The target position, oh, I don't know, let's make it, I don't know how fast he counts, but he'll probably count pretty fast, so let's just make that, let's be cautious, let's make 50,000. Yes, the target position backwards is 0. It's good. Now, stopping tolerance will be I'll just make it really big, because I don't really know how precise he stops. It should be pretty precise, because I wrote 2000 in last semesters and it should have worked, but I'm not sure. And the overlift, so that we actually see it, I will also put at 10,000, so that he actually does move a bit. Force that to 0. Very good. Okay. Load. If I made any, basically any big errors by not attaching variables to stuff that needs to be done, it should pop up now, but it did not, which is very good. Now we can go live and look at that. Okay. X in pos is true, obviously. And X loaded is also true. Why is that? Wait, there is an output here. It wants to move the output says it wants to move horizontal. But why is X loaded already true? Why are you true? Where are you set? Because this guy is true. And this guy is running because the finished variable because this guy already says he finished. Okay. Well, there is another problem that I have not thought of. The y-axis obviously starts in its retracted position, so the conditions for this block are after starting the program are immediately true, which isn't really helpful. I can fix that, but it's already 10. It will be 10 in half an hour, and I'm pretty tired already. So I'll probably call it a day here, and next time we'll fix this block and we'll test it. After that, we'll need to work on the automatic zeroing of the axis, because right now they will not do that when you start it up. So we will probably need to do something with the system of the purple blocks that are called by the system. But more of that in the next stream. I thank everyone that is here, was here, and will be here for watching, and I'll probably stream either tomorrow or Thursday. Depends on my work hours. Yeah. In any case, thanks again and bye.